Just like we have linear equations, we have linear congruences. Okay, so what does that mean? Ax is congruent to B mod M. So here A, B and M are fixed integers where M is greater than 0 and X is an unknown integer. Okay, what we have to do is to figure out the X. When we figure out the X value, we find the solution of the linear congruence. So solution of linear congruence means the value of X such that the statement is true, or in other words, M divides Ax minus B. Okay, let's look at this with an example. X plus 50 is congruent to 39 mod 7. Okay, so here what we do is we take 50 and 39 and figure out the smallest value for this in mod 7. So 50 can be written as 7 times 7. 7 comes from here and we figure out the multiple which takes it nearest to the 50, and whatever is remaining, that becomes the remainder. Okay, so this implies that 50 is congruent to 1 mod 7. Similarly, 39 can be written as 7 times 5 plus 7 5 is 35, so 4 is the remainder, which implies that 39 is congruent to 4 mod 7. So therefore, X plus 50 is congruent to 39 mod 7 implies X plus and 50 is congruent value 1 is congruent to 39's congruence is 4 mod 7. Now what we'll do is we will subtract 1 from both the sides. So we end up with X is congruent to 3 mod 7. So we have got the value of X. How do we verify that it is correct or not? So let's figure out that. So we have X plus 50 is congruent to 39 mod 7. Now X is 3 mod 7 plus 50 is congruent to 4 mod 7. Let's take 3 mod 7 to the other side. What do we get? We get 50 is congruent to 4 minus 3, that is 1 mod 7. And now we can easily figure out whether 7 divides 50 minus 1, that is 7 divides 49. And the answer is yes, 7 does divide 49. So that means this is the correct solution. Okay, now for this, let's look at a theorem. If x1 is a solution of Ax is congruent to B mod M, then Ax1 is congruent to B mod M. Okay, now here we are given that x1 is a solution, so which means x1 is congruent to x mod M, right? And if we multiply both sides by A, we get Ax1 is congruent to Ax mod M. And we are already given that Ax is congruent to B mod M. And remember, congruent modulo M is an equivalent relation, which means it is transitive. Since it is transitive, what we can write it as is Ax1 is congruent to Ax mod M and Ax is congruent to B mod M. That means Ax1 is congruent to B mod M. So we can write this as Ax 1 is congruent to B mod M, and this is what we had to show. Okay. Now let's look at another aspect of linear congruences. Suppose x1 and x2 are two solutions of the congruence AX is congruent to B mod M. If x1 is equal to x2 mod M, then x1 and x2 are called congruent solutions. Okay, let's look at it with an example. Let's say 6x is congruent to 2 mod 4. Let's see. Let's use hit and trial method. So let's say x is equal to 1. Then what happens? 616 minus 2. Is it divisible by 4? 4 divides 4. So this is a solution. X equal to 1 is a solution. Now what about x equal to 2? 4 divides 6 to 12 minus 2, which is 10. So 4 divides 10? No. So x equal to 2 is not a solution. Now let's look at 3. 4 divides 6 3s 18 minus 2. That is 4 divides 16. Yes, it's a solution. Okay. So now 1 and 3 are solutions. But now let's see whether 1 is congruent to 3 mod 4. Okay. So which means does 4 divide 1 minus 3, or in other words, does it divide minus 2? No. So 1 and 3 are called incongruent solutions. Okay. Now let's look at x equal to 4. 4 divides 6 times 4, 24 minus 2. That means 4 divides 22. No, it is not a solution. But what about x equal to 5? 4 divides 6 5s 30 minus 2. 4 divides 28. Yes. Now let's compare 1 and 5. Are they congruent? 1 is congruent to 5 mod 4. That means 4 divides 1 minus 5. So 4 divides minus 4. Yes. So here 1 and 5 are called congruent solutions. Now let's look at the existence. Is there any condition by which we can say that a solution exists of AX is congruent to B mod M? Okay, so this is there as a theorem. The congruence AX is congruent to B mod M has a solution if and only if the GCD or HCF of A and M divides B. Okay, so here you have A and here you have M. If its GCD divides B, then we can say a solution exists. Okay, let's prove this. Let D is equal to the GCD of A and M, and let AX be congruent to B mod M has a solution x equal to x1. Then in that case, we can write this as AX1 is congruent to B mod M, which implies M divides AX1 minus B, which implies AX1 minus B is a multiple of M, where K belongs to the integer number set, which implies B is equal to AX1 minus MK, right? AX1 minus K. Now, let A is equal to A1D and M is equal to M1D. Basically, what we are doing is how we figure out A1 and M1 is that we have A and M, we divide that by D, that is the GCD, to get the A1 and M1. Okay, and A1 and M1, they belong to the set of integers. So now we can write B as A. Instead of writing A, we write A1 D x1 minus, instead of M we write M1D. Okay, and here if you notice D is common, so D we can take it out and write it as A1 x1 minus M1K. So now here you notice that B is equal to a multiple of D. So therefore D divides B, right? Which implies if a solution exists, then it is necessary that D divides. Okay, now let's look at it the other way around, converse of this. Let D divide B, and here all the alphabets mean the same thing as in above. So which implies D is equal to B1 D. Here B1 belongs to the set of integers. Okay, now here comes the tricky part. D we can write it as, because D is, remember, the GCD, can be written as UA plus VM. Why? Since D is the GCD of A and M. Okay, DB1. Now we multiply the whole thing by B1. So DB1 is equal to UAB1 plus VMB1. Now we can write this as, now let's do this. We already know B1D is nothing but B. So B is equal to, let's do the grouping, UB1 plus MVB1. Okay, now let's keep M on one side. So we'll end up with AUB1 minus B is equal to minus MVB1, which means what? Which means M divides AUB1 minus B, right? This whole thing is nothing but a multiple of M. So M divides this. Okay, which implies AUB1 is congruent to B mod M. So here, remember, we started off by saying AX is congruent to B mod M. That means X is equal to UB1 is a solution. So here UB1 is not the important point. The point is there is a solution. And that solution is only possible because of this starting point. So therefore, if D divides B, then it is sufficient to say that AX is congruent to B mod M has a solution. Okay, now with a few points. If D, that is the HCF or GCD, is equal to 1, then in that case there is only one solution. If D divides B, then in that case there are D distinct solutions. And if D does not divide B, there are no solutions. In the next session, we will solve some problems to practice these things. That's it for now. Bye.